Very exciting.
Thank you.
Thank you very much. So next presentation is, do you want to use this one? Is Kyle Chard from the Computation Institute at Argonne National Lab and University of Chicago. And Kyle is software engineering, and he'll talk about DTI image processing pipeline and cloud computing environment. So,
well, thank you, Mike, and thank you for inviting me over here. So as Mike said, I'm part of the Computation Institute, which is a joint venture between the University of Chicago and Argonne National Lab. I work primarily on the Globus project, which is a grid computing distributed system toolkit. Okay, so as we've heard today, there's a bunch of people out there doing DTI analysis that are composing complicated pipelines and workflows out of a number of different tools. We've also heard about a lot of these tools today. And you can see that list there, that a typical analysis is going to involve things like QC, registration, marking ROIs, trying to fiber track and get average values for things like FA and MD. But constructing these analyses is quite complicated. You've got to go and find the tools, you've got to go and find the data, you've got to select the data sets that you actually want to analyze, you need to orchestrate it all together and make it work in an end-to-end pipeline. So we've also heard today that we're making good progress on the data side of things. So we've got these CDEs, we've got data formats that allow us to communicate between different tools and platforms and programs. We've got various repositories, protocols, metadata standards that are all making it easier for us to actually work in this space collaboratively. But I think the thing that we now need to look at is developing infrastructure that reduces the barriers between the tool developers and the people using these tools, the clinicians and the researchers. So part of my group, led by Ian Foster at the Computation Institute, has a goal of trying to enable big science for small labs. So basically what he observes is that we have exceptional infrastructure for the 1%, for the big labs out there that are doing really great research, but 99% of the research is composed of smaller labs that don't have the resources, the computer experts, the statistical experts that can come in and really build them up to a level. So they end up spending a lot of their time working on things that perhaps take away from their core research. So just quickly, we went through and had a look at sort of how many of these analyses are formed. So most people have some sort of repository out there that collects the data from scanners or their post-processing, things like FitBur, IntBur when it's up and running. When researchers want to come and do studies, they might query their database, they might get results directly from scanners, and then they want to go about doing some sort of DTI analysis. So they'll generally look in journals, they'll consult collaborators, they might even Google for ways to compose these pipelines for the tools that they should be using, for the settings they should be using, for the data formats they should be using. They'll download these tools onto their laptop, they'll compose their own pipelines, they might script them, they might use some sort of pipeline engine like Lonnie or MIPAV as we heard earlier, and then when they're happy with their sort of ad hoc pipeline, they'll then parallelize it or run it on multiple clusters on their own resources within their lab. When it comes to changing the protocol, adapting it for new tools, they need to go back, look at their existing workflow, their batch script or whatever. They have to modify it, they have to reinstall the new tools, make sure it works again, and they rerun the script. So there's inherently a few flaws in that process. I think it's ad hoc, it's manual, there's a lack of standards, it's very difficult to transfer knowledge both internally within your group, say if your postdocs leave, for the next postdocs to come in and take over, and also externally when we're publishing papers, how are they able to verify, reproduce, and build upon your research? So what we propose is building some sort of platform where researchers can more easily experiment, where they can use, there's a typo there, but best of breed tools and pipelines, where they can do away with the sort of overhead of installing and managing the infrastructure and the tools themselves. And we ideally would like to abstract those low-level details so they don't need to spend their time on it. So basically, the last line there says we want to make the existing tools and these common analyses mundane building blocks on which we can continue to develop. So as part of our work, this is a bit I know less about being a computer scientist, we've developed a couple of pipelines with the goal of investigating the feasibility of using DTI in clinical practice. So one of the big things we tried to do with this work is focus on automation. So we wanted to automate the calculation of metrics, and we wanted to automatically generate the ROIs instead of having manual ROI drawing and things like that. We wanted to use existing tools. We didn't want to get in there and create our own tools because, as we mentioned, there's a myriad of great tools out there that seem to do the job for other people. And we wanted, this is the bit where I get a bit more interested, we wanted to look at how we can scale this out over increasingly large data sets. We can do it efficiently and cost effectively. So our DTI study, which we're writing a paper on at the moment, explores the reproducibility of 20 subjects with 4 scans, basically using our automated pipelines. So this is one of our pipelines. You'll see that it has the sort of quality control, eddy current correction at the beginning. It does some brain extraction, does linear registration, and then we use DTI fitting with FSL and Camino, which we heard about earlier. We transform it to the M&I space and extract FA and MD, average FA and MD values. So we can automatically do all of this and get some tabular format at the end. We also have a second pipeline that I think doesn't align to T1, but it's pretty similar. So those details will be in the forthcoming paper. So when we started doing this, we went through 3 different approaches for how we can actually build these pipelines. So we started with a script-based approach, where we tried to write bash scripts and then run these on machines. We found it to be quite difficult in that we had one machine that one of us had to sit there and start, or we wrote a script that would run multiple in a row. We were using XNAT within the group, so we thought we might as well try out the XNAT pipeline engine. So we took our scripts, we wrapped them in XML, included them in XNAT, and dealt with that. So I think XNAT is a great image repository, and we continue to use it. But in terms of its support for pipelines, we found it to be a little bit restrictive with what we could do. And parallelizing was somewhat difficult as well. So the last thing we did was we looked within our group. So we've just had a recent push within our group to develop software as a service for genome analysis. So these guys have huge data sets, as was mentioned by Matt McAuliffe earlier. So the advantage of this is it's a web-based platform that runs on the cloud that allows us to scale out analyses so we can deal with like peaks and troughs of actual usage. So when we've got a lot of analysis we need to run, we can scale it out and run it pretty quickly. And when we don't have much to do, we can retract our infrastructure and not pay for the overhead. So we have a graphical interface that basically I can use from my machine to run all these tools remotely and construct these pipelines. So this is a quick schematic of what we've got. So on the left here, we have a bunch of endpoints, which might be my laptop, it might be our XNAT repository. Running on Amazon Web Services, we have a sort of core infrastructure that's Galaxy-based. So Galaxy is a pipeline engine. Condor for scaling out jobs over the dynamic worker pool, which you see on the right. We have Globus Transfer for providing high-performance, reliable, and secure data transfer between endpoints, so we can move data between our repository and our cloud infrastructure without us needing to be in the middle of it. And we have a shared file system so that we can use all of this stuff over our dynamic worker pool. So I'll quickly show you how this works. So we have researcher A sitting in Institute down the bottom there with his laptop. Can query our XNAT repository, which sits also in our university, and start a transfer of the data sets that are of interest to him. So you can basically browse that, start a transfer, and then he can walk away from his machine, and that transfer is going to keep going. He can turn his machine off, and that transfer will keep going until it's finished, and you'll get an email saying the transfer is complete. He can then come to his Galaxy instance, so he has a web-based instance, he just logs online. He can compose a pipeline out of the tools that he has locally, and he can choose to run it. So when he chooses to run it, we pass it to some sort of scheduler that looks at the policies defined by the group, so whether or not we want to spend money on instances, how we want to balance cost and performance. So this will actually go out there, if we've tuned it to run every job as quickly as possible, it'll go out there and work out how many machines we need. It'll instantiate them from Amazon. It'll go and install the tools that are required for the pipeline on them, and then we'll pass the job to Condor, which will actually spread the jobs out to run on each of the machines in that dynamic worker pool. So that's showing the jobs running. So this is how it actually looks to the user. So this is the first part through the, so you see it's Skin Globus Genomics. It's just a Galaxy instance with a bunch of different tools in it. So this first one shows you Globus Transfer, so it allows us to go and pick specific things that we want to move to the execution environment. The next one shows how we actually start a task. So this is a very simple, this is just the ECC. So we just pass in the anatomical image and the DTI image. These are the results. To the right, you'll see that we're building a list of data sets or output data sets as we go. So now we're doing DTI calculation, which is just tensor fitting. So we pick the results from the previous one. And the result, we've skipped a few steps here, but that's the result of each of these anatomical image points, ROIs, from the data set that we're processing and their average FA and MD value. And that's a view of the pipeline, a graphical view of the pipeline that allows us to deconstruct things and change them around when we need to. So the piece that we're probably most interested in our group is the cloud computing part. So why do we actually care to use cloud computing? So the advantage of a cloud infrastructure is it leverages economies of scale to give us quite efficient and I guess cheap access to resources. So the good thing is you pay only for what you use. And that might be I can use a machine for 100 hours, or I might want to use 100 machines for 1 hour. So in the work we've been doing, we run these pipelines on our 100 samples. We want the results back quick, and then we can change parameters, rerun it again, and do it quickly. And that costs the same as if we were to run it on our machine back home over amount of time. So it's on demand, it's elastic, and it's, I guess, unlimited to a point. So you see on the right here, we've got a bunch of different layers of cloud computing. So the infrastructure as a service layer is the Amazon layer that we use for the actual computational resources. We layer on top this Globus Genomics layer, which gives us the Galaxy interface and the ability to provision resources. And then at the top layer are services like XNAT and Globus Online, where we can store data sets and transfer them around. So I don't have too much time, so we'll skim through this pretty quick, but there are obviously issues moving to the cloud. So even trying to look at the Amazon page and work out what compute instances you need. How do you balance price against the capabilities? Do you know if you need EBS or instance store instances? It's all very, very technical requirements. How do you select tools? How do you make sure they're going to run on these dynamic cloud environments? How do we manage the infrastructure? How do we manage the analyses as they're running? How do we move data in and out of the cloud? I mean, there's cost things we need to look at there because moving data in and out of Amazon can be quite costly. And while it's nice to say we have unlimited capacity on the cloud, it's not trivial to scale and parallelize applications to take advantage of as many machines as we like. And of course, the big one probably for this audience is the security aspect. How do we keep the data and the computation safe? And I guess, how does HIPAA fit with that? And I know Amazon's doing some work in that regard. They've got some white papers out there about HIPAA, but still a little bit of an unknown. So briefly, we took a look at some of the pricing aspects of running our pipelines that I showed you at the beginning on Amazon resources. So the left side, you see here a selection of some different Amazon instance sizes, and you'll see in the first sort of main group of column the computational requirements. So you see for a large instance, the pricing is next. We're paying 24 cents an hour for 2 CPU cores and 7.5 gigs of memory, whereas at the bottom, we're paying $1.64 an hour for 8 CPU cores and 68 gigs of memory. You'll also see on the right there that Amazon has a couple of different pricing strategies. So they have this fixed price that you can always get on the left, where you can always go and reserve a M24XL for $1.64, but they also offer a spot price, which is a fluctuating price based on supply and demand, or loosely based on supply and demand. So you see there's some significant advantages with using the spot pricing for these for the big instances. You're paying only 14 cents an hour. But when you do that, Amazon reserves the right to kill your instance at the end of the hour if the spot price increases. So you also saw back there, some of these ones have quite significant differences with their spot price between minimum and max, like M2 extra large goes from 3 cents to 35 cents. And you see here, this is a graph of the spot price over time. So the top one is an M1 extra large, and you see there at the end it gets quite volatile. It's getting up towards $6, I think. $6 an hour, but for less used instances like the M3 extra large, we're getting pretty flat performance. So knowledge of that and understanding the pricing can really help us to optimize our analyses. So here's a quick graph showing our pipeline number 1 running on one of our data sets. So the bar graph is showing the time in minutes for an EBS and an instance store instance. So you'll see with a large, it's taking upward of 100 minutes, whereas when we bring it down to some of these bigger instances, we're getting it down under 40 minutes to do one of these analysis. You'll also see the line graph layered over the top shows the cost per subject, so how much it's costing us to analyze one of these. The black line is the on-demand price, and you'll see there that the blue line is the spot price instance. So you'll see that we can get the price per subject really quite low if we take advantage of spot pricing. And if we know the spot price market, we can be smart about which instance sizes we pick. You'll also notice that the performance doesn't increase as the size of the instance gets bigger. So we saw before the M24XL had 68 gigs of RAM, and I think it had 8 cores. So the problem with a lot of these analyses is the tools we use don't take advantage of things like that. I can throw as many cores and as much memory as I like at one of these applications, and it's not going to increase it. when they don't take advantage of multi-cores, and they have memory ceilings that they don't go beyond. They don't need more than 10 gigs to run some of these. So we looked at this and we adapted our algorithms to use multiple deployments per node. So here we're running on an M2 XL, I think we're running about 10 analyses at the same time. So we've adapted our scheduling policy to basically force more jobs on the bigger nodes, and that we have a simple list of sort of the mapping between the instance and how many subjects we can run on it. We do incur some cost for the startup. So this graph just quickly shows on the left is when we have to create a new Amazon node and contextualize it. So you'll see there's some queuing time, there's some spot price time to go and find a good node at a cheap price, and then there's the contextualization cost, which is going out and putting all the software on that node that we need for it to run. On the right is what happens if we manage to get an existing worker that's already set up with everything we need. So very briefly, I will mention Globus Online. So as I said, it's a third-party data transfer system. So basically, you can go online, you can fire these requests to move data between two endpoints. It automatically will recover from faults. It's very high performance, so it's much quicker than HTTP and FTP, and it deals with multiple security. So you can have different security credentials at either end of your transfer. We also just released a beta version of sharing, which allows you to share your data sets with anyone who also has a Globus Online account in place. So rather than having to transfer your data to Dropbox, you can take advantage of changing. It's basically like a Dropbox interface that works on top of your existing storage system. And this is a quick graph that shows you the performance of Globus transfer as files get bigger compared to FTP and HTTP. So this is why we chose to use Globus Online for our transfers between XNAT and our cloud infrastructure. Briefly, I think the big point is that the structured pipelines can really simplify creation and execution. I think it provides a way that we can structure things and share them and maybe be able to build upon and transfer knowledge a little bit more easily. By outsourcing to the cloud, we managed to bring our analysis time down from weeks for our 100 scan subject to less than $5 for an hour, so 5 cents subject. And the things we're investigating next is how can we deliver this as a service? How could we apply the Globus genomics type model to imaging where we subcontract out this sort of functionality where people can use it and pay only for what they actually use. And we also want to develop tool sheds for sharing tools and pipelines. So I thank Mike, Ian Foster and Steve Tiki at Globus Online and the Globus Genomics guys for helping out with us over the last year or so. Thank you.
Thank you very much, Kyle. And now for next presentation is from